Besides the kinetics and the molecularity of the reactions, SN1 and SN2 also exhibit different stereochemistries of their reactions. So when we start off with a chiral molecule, there's always the potential of making chiral products. The question is, do we maintain the single enantiomer, or do we get a mixture of enantiomers? And why might that happen? So here I've drawn up two chiral starting materials, and we're going to do an SN1 reaction and an SN2 reaction and examine what effect that has on the product. Now, let's look at the intermediate when we're looking at this SN1 reaction. And let's see what that looks like. So the first step in an SN1 is for this chloride to leave, right? So when that leaves, we will get a carbocation. And this is fairly stable carbocation. Right there, it's tertiary. And you've noticed that I don't draw any wedge or hash on this methyl group. And that's because this group right here is planar. It's flat. Now, what can happen with the iodine? Well, if we're drawing a mechanism, we're going to draw that the iodine comes and attaches to that carbocation. But it could attach either from this side of the molecule or it could come from the other side of the molecule. And depending on which side it approaches, it will make different products. So, just to illustrate that, I also have a model here that I built of this. So here's the benzene ring, and in this place right here, I've put a particular model that has the 3 holes so that we can show that it is a planar, trigonal planar structure. And you'll notice that this molecule is symmetrical. It's flat right here. So we could either approach from this side and attach the iodine there, or we could have the iodine approach from that side and attach there. Now, depending on which side it attaches to, we'll choose between R or S configurations. So, if the iodine comes in from this side, we will make the S configuration, whereas if the iodine comes in from the other side, we'll make the R configuration. And I'm going to set this aside and we'll draw out those two possibilities. So, if the iodine comes from the top of the page into the molecule, then we will form the S enantiomer. So, I'll draw that. So, this is the S enantiomer. And then if the iodine were to come from the back of the page and attack the carbocation, then we would form the R enantiomer. So now the methyl group is up at the top. The iodine is going to be coming from the other side. And here's the R enantiomer. Now, there's nothing in this particular molecule to differentiate from one side or the other. And so we'll get a 50-50 mixture or a racemic mixture of these two. Now, if we were hoping to maintain the stereochemistry, especially if we started with an enantiomerically pure substrate, we may be disappointed when we get a receiving mixture out of the product. Now, there are ways to influence a reaction to, even when it goes through a carbocation, to encourage one or the other enantiomer. And some of the ways that we can do that is if the molecule had a second chiral center, like say we had another chiral center right here on this carbon, then that would have an influence over here with our product because there would be some chirality right here. And it might inhibit the approach of the iodine from, say, this side or the other side. Now, that's not a perfect way of controlling the stereochemistry, but we may get a little bit more of one product versus the other. Wouldn't be a quite 50-50 mixture. Another thing that we could do is if this reaction had a catalyst available to it, and we chose a catalyst that was chiral, that would influence the direction of the reaction. And that's an excellent way to take something that's not chiral and turn it into a chiral molecule, especially since a catalyst is not as much of the mixture. We're not using stoichiometric amounts of it, hopefully. And then there's one more way, which is to use a chiral auxiliary. Chiral auxiliary is a molecule that is chiral, and it's dissolved in the solution with all of the other material, but it does not directly participate in the reaction. So it may coordinate with the iodine, or it may coordinate a little bit here and help block one side or the other, or favor one side or the other. And there are several chiral auxiliaries that gets used, and if you're interested in that, you can look up more information on that. But those are just some of the ways to influence which direction a reaction will go. Now, another thing that we could do is, instead of choosing our conditions so that SN1 is favorable, we could go with an SN2 reaction. Now, an SN2 reaction will maintain a single stereoisomer or enantiomer in the product. So when this happens, we will get just one enantiomer out in the product. So I'm going to draw that here, and then we'll talk about how this happens. So you'll notice that here we've started with the S isomer, and now we're ending up with the R isomer. Now plus some chlorine, or chloride. So how does this actually happen? Well, in an SN2 reaction, this is a concerted process, right? It all happens in one step. And so now we have to ask ourselves, how is the iodine going to approach this molecule, right? Is it going to come from this side, or is it going to come from the other side of the paper? Well, we should know that it's coming from the other side of the paper, and the chloride's leaving here just based on what I've drawn here. So why is that the case? Well, this chloride's a fairly large atom, and the iodine's even bigger. And so steric hindrance is a factor. So if the iodine were to try to approach from this direction, it would run into the chloride and be a little bit blocked. And a lot of times our leaving groups are pretty large, but there's another reason for this. The chloride is a negatively charged ion or species, right? It's a little bit more electronegative than the rest of this molecule. So we're going to have a partial negative charge on the chloride, and we have a full negative charge on the iodine. So when these two interact with each other, they're going to repel, further making it so that the iodine should approach from the other side. So I'm going to draw a picture down here, and I have some model kits to help explain this too. So we're going to start off like this. And that's coming out of the page, and that's going into the page. And then we have our chloride over here. And it's a hydrogen. So our iodine is over here. And it is going to do what's called a backside attack. And the chloride is going to leave. Now, we're going to have a transition state here where the iodine and the chlorine are kind of in the middle here. So I'm going to draw that transition state, and you can see what's happening a little bit here. So we'll have our carbon, and then coming out of the page is our benzene ring, phenyl group. Going into the page is the methyl. And then we have our chloride and we have our iodine starting to interact with the molecule here. And then as we transition over to the product, we make this. We have our iodine here, and it's now bound to the carbon. We have our hydrogen up there. And then we have over here, we have our phenyl group. And back over here, we have our methyl group. So you can see how it's flipped the direction. There's this, like an umbrella turning inside out. Now, I've got some models to help illustrate this a little bit. So let's say that we have, this is our starting material, and so we would have this kind of chirality. And there's our chlorine, our leaving group right here. And we'll have an iodine, and it will come in and it will attack this carbon right here. And that's going to push all of these kind of flat, like our middle object there. So let's say it would look kind of like this, right? So I've put longer bonds in there to indicate that this is kind of forming and that's kind of leaving. And so you can see here how those, the substituents here are kind of transitioning over to the other side of the molecule. And then we're going to go ahead and show what the product looks like, which would be this, right? So now all of these have flipped over kind of to the other side of the molecule there. And that has changed this from an S to an R, or an R to the S, either way. But it maintains that stereochemistry, right? So we have this, we have the backside attack, kind of starts to move over these substituents. And then once this has fully left, the leaving group is left, then we end up with the opposite chirality. And you can see here how these are mirror images of each other, right? So just like that, we've got the orange over here, just like that. And of course, we've done a substitution with this, but now we've moved from one chirality to the other. So that's a big difference between SN1 and SN2. And this is a very important thing to remember, especially when we're designing a synthesis. If we desire to have only one enantiomer, we need to keep in mind that we're going to try to do SN2 reactions rather than SN1, especially when we're starting with a chiral molecule. We'll lose that chirality in the end if we go through a carbocation, which is, again, planar. So no differentiation between one side or the other of this molecule. Now, when we're designing a synthesis, it's important to recognize not only that, yes, we'll maintain a chiral molecule after an SN2 reaction, but it's important to keep in mind that the chirality will flip. So if we start with an S, we will get an R product. Conversely, if we start with an R product, our reactant will end up with an S product. So it's important to keep those kinds of steps in mind when we're trying to go for a particular enantiomer in the product.